If we let u and v be non-zero vectors and let u equal to the sum of vectors w1 plus w2, where w1 is parallel to v and w2 is orthogonal to v, as shown in this picture here, w sub 1 is called the projection of u onto v, or the vector component of u along v. So that is w1 here, and that's the projection of u onto v. It's denoted by w1 equals the projection of u onto v. So whatever the subscript is, that's the vector that you're projecting onto. w2, which is u minus w1, is called the vector component of u orthogonal to v. So w1 and w2 are orthogonal to each other. Notice that w1 keeps the direction of v, but its magnitude is influenced by u. Okay? And then w2 is orthogonal to that. Now, if you were to copy this w2 over here, you can see that u is the resultant vector w1 plus w2, and then you can see why that would lead w2 to be u w1. This is the way that this looks when theta is acute, and this is the way that it looks when theta is obtuse. In order to calculate the projection of u onto v, you can use the dot product. It's u dot v divided by the magnitude of v squared, all times v. And this is a pretty simple calculation. You just have to find the individual pieces and then multiply them by the vector. Remember that the output of this should be a vector, so you are going to actually have to multiply that constant by v. So we've got 2i plus j plus 2k, and we've got 3j plus k. So I'm going to start by finding u dot v, which will be 2 times 0, because there's no I here, plus 1 times 3, plus 2 times 4. So that gives me 3 plus 8, or 11. The magnitude of v squared gives me the square, well, we actually don't need the square root. You can just eliminate that because we're squaring it. We'll have 0 squared plus 3 squared plus 4 squared, which gives me 9 plus 16, or 25. So w sub 1, which is the projection of u onto v, is u dot v divided by the magnitude of v squared times v. So that will be 11 divided by 25 times the vector, and in component form that's going to be v, which is 0, 3, 4. So that gives me 0, 33 over 25, and 44 over 25. And if you need this in vector form, you would have 33 over 25 times j, and I mean unit vector form, plus 44 over 25 times k. So that would be your vector. Now w2, the vector component of u orthogonal to v, is going to be u minus w sub 1. So that will be 2i plus j plus 2k minus 33 over 25j plus 44 over 25k. And remember, we just want to add our like terms. So that gives me 2i minus 8 over 25j, because that's 1 minus 33 over 25. 2 minus 44 over 25 gives me plus 6 over 25k. So that will be my answer. An example of an application of this is a 48,000-pound truck is parked on a 10-degree slope. See the figure here? Assume that only force to overcome is that due to gravity. First, we want to find the force required to keep the truck from rolling down the hill and the force perpendicular to the hill. And we're going to pretend that it says to round our answer to 2 decimal places. So first of all, there is a projection that's happening here, and we'll talk about what that looks like. But we're going to call this force right here U. So U is going to be the force of the truck's weight. And that's going to be equal to some F, which we'll call it F. and that's going to be minus 48,000 J, because the weight of the truck is a function of gravity, and that's looking straight down. Also, we need a vector for the truck right here, and we're just looking for the unit vector in its direction, so we'll let V be the cosine of 10 degrees, and of course this is in degree mode, so make sure if you're using a calculator that you're in degree mode, times I, plus the sine of 10 degrees times J. So A wants us to find the force required to keep the truck from rolling down the hill. So what this is the projection of the force of the truck onto the hill. So what we're really looking for is the projection of F onto V. So that will be F dot V divided by the magnitude of V squared times V. So the F here is negative 48,000 J. And when you find F dot V, you're going to get 0 minus 48,000 times the sine of 10 degrees. And of course, this is a unit vector, so the magnitude of V is equal to 1. So we'll have a 1 here. And that's going to get multiplied by V, which is cosine of 10 degrees I plus sine of 10 degrees J. So this gives me, if I were to, and we can call this V if you like, so this gives me negative 48,000 sine of 10 degrees all times V. And I know that sounds a little bit strange. Why are we going back to just V, which is right here? But we want to know the amount of force. And if we know a vector for the force, the amount of the force is going to be the magnitude of that. So the amount of force will be the magnitude of W sub 1, which is going to be the magnitude of negative 48,000 sine of 10 degrees times V. Remember that this is just a constant, so it's really just the absolute value of negative 48,000 sine of 10 degrees times the magnitude of V, which we know is 1. And this right here, if you type into a calculator, is 8,335.11, rounded to 2 decimal places, pounds, times 1. So it's going to take 8,335.11 pounds of force to keep the truck from rolling down the hill. Now the other question is the force perpendicular to the hill. So the force perpendicular to the hill is going to be W2, that complement that we talked about, which is going to be F minus W sub 1. So remember, F is the negative 48,000 J, and W sub 1 is negative 48,000 sine of 10 degrees times V. So we get negative 48,000 J plus, minus a negative, 48,000 sine of 10 degrees times cosine of 10 degrees I plus sine of 10 degrees J. And this is going to give us, if we group our like terms, 48,000 sine of 10 degrees cosine of 10 degrees I plus 48,000 sine squared of 10 degrees minus 48,000 J. So we've got this part and then this part right here. So the amount of force would be the magnitude of W sub 2, which is the square root of 48,000 sine of 10 degrees squared. Oh, sorry, cosine of 10 degrees also. Sometimes this tablet does not do what I expect it to. All right, sine of 10 degrees, cosine of 10 degrees. There we go. Squared plus 48,000 sine squared of 10 degrees minus 48,000 squared. There we go. All right, these are some really big numbers if you evaluate them, but when you put them into your calculator, all together you get about 47,270.77 pounds. So that would be the amount of force there. Let's talk about work. We know that for a constant force acting along the line of motion, work equals force times distance. In terms of vectors, that means work is the amount of force, the magnitude of the force vector, times the magnitude of the directed line segment that gives us the motion, the distance. So we can think of it as the multiplication of those two magnitudes. Now, when a constant force is not moving along the line of motion, we need to use a projection to calculate the amount of work done. So for example, right here, this is the line of motion, but for some reason this person is pushing up on the object instead of pushing forward. And there's a angle between these two vectors called theta. So work is going to be equal to the magnitude of the projection of F on PQ times the magnitude of PQ. The work W done by a constant force F as its point of application moves along the vector PQ is going to be either one of the following. It will be that projection, or it will be F dot PQ, which is just the dot product form. This can be found from the definitions that we've looked at so far. And basically, you can use either one of them, whichever one is more convenient for your purposes. So this example says a car is towed using a force of 1,600 newtons. The chain used to pull the car makes a 25-degree angle with the horizontal. Find the work done in towing the car 2 kilometers. So what I have is I have a vector along which we're traveling. This is my car. And with the horizontal, we're making an angle of 25 degrees. And this force is being applied, which is 1,600 newtons. Okay, pretend those are straight lines. The distance here for V is 2 kilometers. And that's pretty much all the information that we're given. So I am going to use the F.V version of this, or the F.PQ version of this, because I can calculate that pretty effectively. I know that F is equal to the magnitude of F, which we're given, times cosine of theta I plus sine of theta j. And we're given theta, so that'll be pretty easy to do. So that's going to be 1,600 cosine of 25 degrees I. And if you distribute, you get plus 1,600 sine of 25 degrees j. And I also know that V is a straight horizontal, so V is going to be the vector 2I, or 2, 0. So the work is F dot V, which is going to be 1,600 cosine of 25 degrees times 2 plus 1,600 sine of 25 degrees times 0. So this gives me 3,200 cosine of 25 degrees, which is about 2,900.18. And the units for this are kilometer newtons. And don't let your physics teacher judge me. This is how the book in the Web of Science expects you to leave your units. Anyway, so that's one way that you can calculate work. Again, if you would rather, you can absolutely find the projection vector there and do the magnitudes, but either way is fine, and this is just the way that usually works out the easiest.